Hi all, welcome back to Microbiology Lectures. And today we're going to dive into endosymbiosis or endosymbiotic theory. Before we dive into what is endosymbiosis, some of you may or may not know what it entails. I first want to talk about Lynn Margulis because Lynn was the individual that made it so the scientific community would look at endosymbiosis. And she went through a lot to get the scientific community to even examine it. Okay, so a little bit about Lynn. So she was considered a scientific rebel. She was considered unruling. She was considered to never give up. Some people considered her like appalling in the sense that she was studying something that most people said there is no chance, no way that that's true, and she wasn't going to give up on it. And she had a gut feeling, an inclination, a little bit of evidence that endosymbiotic theory explained how prokaryotes could give rise to eukaryotes, and she went for it. Okay, so a little background about Lynn. A little bit more. So, because she was a woman, first of all, during a time where science was dominated by men, she would get things like this. She once received a message back on a grant application that basically, according to her, she quoted it, "Your research is crap. Don't even bother to apply again." Okay, and that didn't stop her though. Lynn was driven, and for that, the scientific world owes her a lot. We benefited a great deal. So in 1953, at the age of 15, Lynn entered the University of Chicago. That's where she met her husband, who many people probably have heard of, Carl Sagan. Carl Sagan was a astronomer, talked a lot about planets and potential for life off of this planet, whatnot. He was a fairly good scientist. I shouldn't say that. He was a really good scientist. But what made him great, and what made him Sagan a household name, was that he was good at explaining complex ideas in simple words. And so they met actually at the University of Chicago. They got married before she entered Wisconsin to get her master's degree in genetics. And then she went on to get a PhD at Berkeley. And she finished that PhD in 1965. And then she took a job at Boston University and taught there for 22 years until she retired. And, that might not be that interesting, but the interesting piece about it is what she did in Wisconsin and at Berkeley. And it was really, she studied mitochondria. She studied mitochondria during her master's degree, didn't know anything about genetics, and in 1957 genetics was fairly new, but she noticed that in the mitochondria that they had their own DNA that was different than the nuclear DNA, and they had their own DNA, and she wasn't okay with just a generalization of, that means that when the nucleus generates a mitochondria or whatever, that some of the nuclear material is just passed on. I mean, there's all kinds of explanations for why mitochondria might have their own DNA, but she wasn't okay with it. So she then went to Berkeley and studied not just mitochondria, but she studied mitosis and meiosis, and the connection between DNA, nuclear DNA, and mitochondrial DNA, and DNA that's found in the chloroplast, and the potential RNA that's found in ribosomes. And she started drawing these conclusions like, hey, there's a lot of this DNA and there's a lot of similarities between these organisms that we call eukaryotes and prokaryotes. Or I should say, there's a lot of similarities between the organelles of these eukaryotes and prokaryotes. And so Lynn, at the time, she was Lynn Sagan, and then they got a divorce, and she went back to her maiden name. She published a paper on the origins of mitosing cells in 1967, and she was met with a lot of rejection. A lot of people did not accept what she was proposing, that prokaryotic cells gave rise to eukaryotic organisms. This was not the first time that anyone proposed this, because she didn't actually come up with the idea all on her own. Okay, there was lots of historical evidence from this, going all the way back into the 1800s. There was individuals that were proposing the same idea, and the problem that they had is genetics wasn't around. So what they did is they thought, okay, well, the mitochondria is just like a bacteria cell. If the mitochondria is just like a bacteria cell, we should be able to take a mitochondria out of a eukaryotic cell and grow it all by itself, and it should act just like a bacteria. And this was tried by lots of scientists, and no one could do it. No one could pull the mitochondria out and have it grow on its own. Same thing with the chloroplast. If the chloroplast is a lot like a bacteria, a photosynthetic bacteria, you should be able to pull it out and grow it. And even Lynn suggested that we should be able to do this. But the great thing about Lynn and what she had is she had the genetics piece. Okay? Even though it was early on in the genetic movement, and like we had just really discovered the structure of DNA at this time in the 1960s. She had that genetic component. She knew through research that she kept doing that there was this connection between the genes. And she can contribute a ton to science. Lots and lots of books that she published on symbiotic planet, genomes, just all kinds of things. And eventually, after roughly 130 scientific articles about the topic of endosymbiosis, she's known as the mother of endosymbiosis. And she was once questioned. I would like to bring Lynn up because I want individuals, young people, to think about it. There may be roadblocks in your way, and there may be people at times tell you your idea is stupid and don't ever apply again, or your research is terrible, or whatever it is that you're doing is not valuable. And in fact, even after she had published multiple books, multiple articles, etc., she was once asked, Lynn, why are your ideas, or how do you feel about your ideas being so controversial? And I just find what she wrote or what she said was, I don't consider my ideas controversial. I consider them right. I consider them scientifically supported. I consider them true from a scientific perspective. Okay? And I think that's just really powerful. For Lynn, she didn't care how many roadblocks. She didn't care how many people, put her down and tell her that her ideas were terrible and that it was wrong and whatever. And now the endosymbiotic theory is the theory that we accept based on tons of evidence. And so now I'm going to talk about that evidence. Okay, it's also called symbiogenesis or symbiogenesis, and that's really the idea is that the origin of eukaryotic cells came from prokaryotic organisms. Okay, so we talked about this a long time ago, that prokaryotic life popped up about 3.8 billion years ago. Okay, the formation of the Earth is 4.6, 4.5, somewhere in that range. And then life pops up at about 3.8 billion years ago. And we go for quite a bit of time, okay, roughly 2 billion years, with single unicellular organisms, no membrane-bound organelles. Everything would be classified currently today as prokaryotes. Okay? And then symbiogenesis occurs, or endosymbiosis occurs, at about 1.8 billion years ago, 1.9, 1.7, somewhere in that range, billion years ago, we see eukaryotic cells pop up. Okay? And the lines of evidence are overwhelming now that we have DNA. Okay? Before DNA, it was just look at the structure of mitochondria. What? Mitochondria have their own ribosomes? Wow, that's weird. Look at mitochondria have multiple membranes, and look where ATP synthase exists. It's in the membrane, much like bacteria. Okay, chloroplast, same deal. Like, look at these structures that are, they have their own DNA. We knew they had their own DNA and everything. But once DNA, we could analyze DNA, then we could see that the DNA of mitochondria, the DNA of chloroplast, is unique to that structure. It's not nuclear DNA. Okay? They have their own ribosomes. Those ribosomes are nearly identical to prokaryotic ribosomes. They're not eukaryotic ribosomes. Okay? Their ribosomes are 70S ribosomes. Okay? They're not 80S ribosomes. So even though we say eukaryotic cells have 80S ribosomes, well, that's true, but the ribosomes that are associated with the mitochondria and the chloroplast inside eukaryotic cells is a 70S ribosome. Okay? They have double membranes surrounding both organelles. Okay? When they multiply, when you increase the number of mitochondria in a cell or chloroplast in a cell, they multiply by binary fission. Okay? The similarities were outstanding, and then once we start figuring out the DNA, we can start looking at DNA sequences. And now we can start saying, all right, how closely are the DNA sequences of like eukaryotic ribosomes or eukaryotic mitochondria, how closely are they related to known bacteria out there? Okay? And we figured it out. Like, there are known species of bacteria that have very similar DNA sequences to the mitochondria. Known species of bacteria that have very similar sequences to chloroplast. And so through all this evidence and the fact that Lynn wouldn't give up, we now have a very good explanation for the connection between prokaryotic and eukaryotic cells. Now, there's always like chicken egg situation, like which one kind of came first? Like, was the nucleus first, and then after the nucleus the mitochondria was consumed by the organism? So nuclear material came first, membrane-bound nuclear material came first, or membrane-bound powerhouse came first. And this is debatable on chloroplast also, same kind of deal. So really, the cool thing about it is Now, instead of saying there's no way there's a connection between prokaryotic organisms and eukaryotic organisms, that prokaryotes could never gave rise to eukaryotic cells. Now, instead of saying that, instead of doing that, the scientific world is now, yeah, this happened. Now let's find out which came first. The chicken or the egg. We know chickens lay eggs. So we know that prokaryotic cells are linked to eukaryotic cells. We're just not sure which hypothesis is correct yet. Okay, so with that, we'll come back and we'll talk about other techniques that microbiologists use to analyze the microbiology world. We'll talk about serial dilution, we'll talk about plating techniques, we'll talk about different types of media that we can grow different organisms on, so we can get at the medical piece, but tie that medical piece back to the ecology or morphology of the organism. See you next time.